It works. Hi, welcome to my talk. My name is Alexander Chatzizacharias. A little bit of a tricky last name, but there was another Greek person here, so there are at least two people that can pronounce my name here, so that's great. I work as a back-end software engineer at a company called J-Driven. I have a couple of hobbies. I like bouldering. I have a way too expensive Magic the Gathering collection, which I shouldn't be proud of, but I'm kind of proud of. And I'm a huge gaming nerd. I really like playing games. Any other gamers here? Sure. You'll probably notice my love for games during my presentation. I work for a company called J-Driven. It's a very small consultancy in the Netherlands. And I just consult left and right. At the moment, I'm consulting at the Port of Rotterdam at rootescanner.com. And that's pretty much all I had to say about myself. I mean, you all were there, I think, last year during D-Day when OpenAI released ChatGPT and introduced us to the world of large language models and AI and the beauty of it. And I was there as well. I was reading it. I was playing with it. And I was like, okay, what the hell? How does this work? So I mean, you start Googling, okay, how did they do this? Transformer models, machine learning, et cetera, et cetera, et cetera. Well, unfortunately, I didn't really have the billions backing me to really get into large language models like OpenAI has. But there was one term that kept coming back whenever you started reading about large language models or AI applications or how they work. And that was vector databases. So I kind of went and focused on that. How do they work? What are they? How are they different than your standard relational database? And I kind of want to show you guys what I did to kind of teach myself what vector databases are, how they work, and who knows, maybe you can use them at your project as well and revolutionize the industry. Who knows? Before we start talking about vector databases, there's one term that's kind of important that everybody needs to understand, and those are vectors. Are there any mathematicians sitting here? I asked this at CERN, I know. Okay, great. If I say anything stupid, please correct me. I'm no mathematician myself. But yeah, vectors are a mathematical construct. And if you see them in papers or whatever, typically you'll see well, I can point to that, but it doesn't really matter. You see a letter with an arrow on top of the letter. And that means that something is a vector. And vectors are constructs that are very good in representing or encoding a distance and a direction. And that is mostly what they are used for. I don't know if anybody makes games here or have dabbled in game development, but using vectors in game development is the way to go to, say where your objects need to be in a 2D or 3D space. And a vector has a certain dimensionality. A lot of times it's 2 or 3. So this is a vector with 2 dimensions, and this is a vector with 3 dimensions. But vectors can actually have as many dimensions as you want. This, for example, is a vector with 8 dimensions, and it can go up to thousands and thousands of dimensions. I know there are companies out there that are experimenting in using vectors with up to 1 million dimensions, so that's kind of cool. But for the developers here, which should kind of be almost everyone, I think, you might notice that this looks a lot like an array, right? Just an array of numbers. And that is how we, at least in software development, we can think about vectors. They are an array of numbers where the dimensionality of the vector is the size of your array. It's of course not, exactly correct, mathematically speaking, but it gets you going. So how do we use vectors? Roughly 10 years ago, 11 years ago by now, people thought, okay, if we have a piece of text like this, then we can translate it into its so-called vector representation. And after text, they started doing the same with images. If we have an image like this, then we can translate it to its vector representation, which would look something like this. And it goes much further. Now that they're vectorizing things from audio, 3D models, and it goes so on and on and on. Everything is they're trying to vectorize right now. And they did that through the use of machine learning. So machine learned models that taught themselves how to grab a piece of input, and the output would be the vectorization of that input. And those we call embedding models. So if you read online something about embeddings or embedding models or embedding endpoint or whatever, that means it's an endpoint or a function or something that grabs input and outputs vectors for you. There are a lot of those models right now. The first one was Word2Vec, 2013, released by Google. And Word2Vec worked okay, but it had a big problem. It didn't really understand context. So a word with different meanings would always have the same vectorization, which kind of makes it almost useless, you could say. Glove, released a couple years later, had the same issue. But a couple years ago, we had the transformer revolution, so to say, and transformer models came out, and transformer models actually could vectorize text with context. So different pieces of text or the same text in different contexts would have different vectorizations. And that really enabled, these vectorizations to be used for large language models or AI applications, stuff like that. And right now, we are getting more and more models that can vectorize different sources of input, like images and text, into the same vector space. But what that is, we'll get into in a little bit. All right, so that in very short, those are vectors and how they're used. So now onto the second word in these two words, databases. Everybody knows what a database is, right? Right? Okay. But what is a vector database? Who here uses like Postgres in their day-to-day? All right. Oracle databases? I have an opinion, I won't share it. A vector database is really a purpose-built database. It has only one purpose, and that purpose is store vectors and retrieve those vectors as quickly as possible. Do not use it as a time series database. Do not use it as an event sourcing database or something like that. Is it possible? Sure, everything is possible, but you really don't want to go there. It can store and index really high dimensional vectors. So right now, a lot of the dimensions you'll see are 512, 1024, power of 2 dimensionalities. But they're really scaling up into, well, hundreds of thousands, even millions dimensions. And they index and they retrieve your vectors using nearest neighbor search algorithms. Think of k-nearest neighbors, stuff like that. You might be familiar with those kind of algorithms, might be not. And of course, you can store metadata alongside those objects for you to actually build applications around the data you store in your database. So very plainly speaking, you can think of the vectorization of your object being your ID for an object. And the tables in a relational database would be the metadata. Okay, let's say you have a product owner or a manager that is a little bit tech illiterate, comes to you and is like, I heard about this thing, vector databases, it's amazing, everybody talks about it, we gotta use it, what is it? Then I would answer with, it's a database that facilitates effortless and swift semantic search on your data. Semantic being really the key word here, right? So if you wanted effortless and swift search on your data, you probably would be looking at Elastic or something like that. But if you really need a semantic way to search through your data or categorize your data, then vector databases are probably the way to go. And that does mean that vector databases are not inherently AI. Right now, they are kind of synonymously talked about with AI applications because, I mean, they are being used mostly by AI applications, large language models, and the such. But by themselves, they have nothing to do with the AI. There are no machine learning models in there. It's just a specialized program that indexes vectors for you and can retrieve vectors for you very quick. So if you, for example, want to store the whole Minecraft world in a vector database and retrieve it as you walk around, it's possible. It doesn't work very well. I tried, but it's possible. when you index things in a vector database, there are a couple of ways, a couple different algorithms you can choose, or you can write your own if you're very adventurous. For example, linear search, which is, you can imagine, doesn't necessarily scale very well if you have millions upon millions of vectors. Or, for example, gain nearest neighbors. But most often you'll see approximate nearest neighbor indexing algorithms and retrieval algorithms. Shout out to Spotify. I don't know if anybody from Spotify is here. No. And they named their algorithm approximate nearest neighbors, oh yeah. And my personal favorite is hierarchical navigable small worlds, which sounds like you have a little world in your database, which makes me happy. But it's a pretty cool algorithm if you read into the paper. And once you want to retrieve a vector out of your database, they're going to do a so-called distance check on the vector that you're going to search from and try to find the closest vector to there. And the distance check, you can do that, for example, through Euclidean distance, which is typically what you'll see. Or similarity. Who knows the difference between distance and similarity? Okay, let's hope I say this correctly. If you're asking for the distance, you're asking how far things are from each other. And if you're asking for similarity, you're asking how close things are to each other. Now, some of you might think, okay, this is exactly the same. What are you talking about? The distance, if it's close to 0, that means things are close, very close to each other. The similarity, if it's close to 1, that means that things are close to each other. So it's a little bit different. And then you can use different kinds of distance metrics to actually do the distance check. And very important thing to know, in vector databases, distance calculation and indexing always happen within the same vector space. And you can define your vector space by schema or by table or by object, and every database has a way of defining a vector space. You can really see it as a table in a relational database. It doesn't have a lot of use except for one very important thing, is they make sure that the vectors stored within that vector space are always of the same dimensionality. So that when you search for vectors, you won't, for example, input a vector with 512 dimensions and try to find a vector with 384 dimensions. Mathematically speaking, it's possible to do that check, that distance check, but you wouldn't get very good results. So they're saying, okay, define your vector space, always the same dimensions, then we can ensure that at least the math behind the distance checks and everything we do checks out. Now try to visualize the vector space of one of my data sets a little bit. And I am someone that takes things quite literally, so when I hear vector space, I am like, okay, this is space. So this is one planet I created, or this is one data point in the database of one of my vector spaces. Anyone that played Starfield? No one? Oh, poor Bethesda. And as you can see, you can fly around and you'll see more data points and more planets, and the textures are generated through the vector is a vector of an object, so it's always the same. Kind of cool, if you ask myself. But I will admit, this might not be the most user-friendly way of going through your data sets. It's the most fun way, but these are all the vectors in this vector space that are right now in the database. And what you see are clusters forming. So if you look here, this is, for example, a data point called whip. And next, close to it, there is something called a slingshot. And here is a shuriken. So for the ones that know martial weapons very well, you already saw that these are pretty similar objects to each other. That means semantically speaking, they are similar. So they end up closer, indexed closer to each other. And that means if I search, for example, a Japanese throwing star, there is a big chance it will land somewhere here close and will get me back the shuriken. And that is what you want with a vector database. That's what you're gunning for. Pun not intended. All right. If you think, okay, this is cool, which databases do I want to use? These are the biggest databases right now. Postgres has an add-on, of course, pgvector that you can use. I'll be honest with you, it's really a gold rush out there. People are releasing new databases every day, feels like. It's really very hard to keep track of these databases and which one are new and which one are end of life or stuff like that. Of course, if you want to play with these databases, you want an open source, probably. So everything on your right side is open source. Pinecone and Redis are closed source. At least the vector database of Redis is part of their Redis stack, which you have to pay for. Elasticsearch or Elastic is a little bit weird. On their website, they are like, yeah, we are open, but actually not that open. So I don't really know if it's actually open source or not. I think you have to pay for it, but I'm not sure. Very cool thing some databases offer are so-called built-in embeddings. That means when you enter your data in the database, they will automatically embed that data for you into its vector representation. If a database doesn't have built-in embeddings, like everything on your left, that means that you have to do a call to OpenAI or Hugging Face or some external service, or use your own embedding models to create a vectorization of your objects, and then you can insert them in the database. And the ones on your right offer that out of the box, which is a cool thing to do, I would say. Of course, they need to earn money somehow if they are open source. So almost all of them have a managed service where you can just click, 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 goes online, and you can play around. It is quite expensive, though, also from experience. And for pgvector, you can use Supabase. They have a managed service around pgvector, which you can use. Finally, you want to be able to query that data out of the databases. All of them have a Python CLI or a Python client, by the way, because Python is king in AI land. Some of them have a REST API, which you can call. Others have a JavaScript client or a CLI. Some you can call through SQL to retrieve your vectors or store your vectors. And finally, Vespa uses YQL, which is, I think, Yahoo querying language, which is a choice. All right, so that was a little bit how the landscape looks like. By the way, all these databases, they kind of do pretty much the same. They will all tell you they're the fastest one, they're the best one, they're the whatever one, but they all kind of do the same. So if you start experimenting, just grab an open source one and grab the Docker image of that database and just start throwing things in there. That would be my advice. Okay, so let's implement our own search. We're going to be using VV8 for persistence. I have a Spring Boot Kotlin backend, and I have Unity as a frontend. Kotlin, because it is the superior GVM language, changed my mind. And Unity is a little bit of popular bad boy right now in the industry. They've been doing a lot of interesting choices, let's keep it at that, with their monetization and laying off people. But I'm quite proficient with it, so that's why I keep using them. And I don't pay them anything. So I chose VV8 because it's completely open source. That's quite nice. The documentation is actually quite decent. And if you play with a lot of startup projects or startup products out there, you'll notice one thing you'll really notice a lot of times: the documentation is, let's say, lacking. But their documentation was pretty nice, and their Java client was also pretty nice, pretty straightforward. And it's completely modular. And it can run completely offline. So everything right now runs just on my laptop, nothing is online, which is quite handy if you give sessions like this in maybe bunkers or cinemas or whatever. All right. And it's a pretty simple architecture that everything uses. Our Unity frontend will be calling our backend through REST HTTP calls, and the VV8 Java client library is doing REST calls or GraphQL calls to the Docker container. Now, if you're an architect, you see this, you might ask me, okay, but why do you have a backend in between? Why don't you just go immediately to the Docker containers, where I say I'm a backend developer, and I mean, if I see a chance to add an abstraction layer that's not necessary, I'll take it, god damn it. All right. So today we'll be using cosine distance as our distance measuring, hierarchical navigable smart worlds as our indexing algorithm, and we'll have some models, BERT models, resonant 50 models, and clip models for all the embedding that we'll be doing. So what is cosine distance? Well, it's 1 minus the cosine similarity. Okay, that was it. No, and the cosine similarity is this beautiful formula. I don't necessarily expect you to memorize this, but what's important is if it comes out 0.0, that means two vectors are identical. If it comes out 2.0, that means that two vectors are opposite to each other. So if you have a Java class and a C# class and you vectorize them both, they'll be 0.01 maybe, because there's basically the same language, right? And if you have a JavaScript script and a Java class, then they will be? Yes, that will be quite opposite, unless you did some really dirty Java programming. All right. And then for our indexing, we'll be using hierarchical navigable small worlds. It's a little bit of a tongue twister, which is a little bit trickier to explain. So I tried to do it like this. So these are all the data points that we'll be want to be putting in our database. And every time a data point enters the database, the algorithm is going to do a proximity scan around it to find X amount of nearest neighbors. And then it will connect itself to the X amount of nearest neighbors. So you're basically building a neighbor graph or a proximity graph, or it has 1,000 different names, I think. But basically, in our case, we'll search for the 3 nearest neighbors, connect to those neighbors for our neighbor graph, and then keep going. Eventually, more and more points will be added, and the algorithm will create a second layer on top of the first layer. And it will duplicate one of the points and do the same in the second layer. So it will create a subgraph of your real data set or your real graph on top of the which is smaller, and will basically do the same. And the more points you add, there's again another random chance that those will be duplicated into a third layer in our case, and do the same. So I've tuned the algorithm that the chance is 0.33 from the bottom layer to the middle layer, and then 0.2 from the middle layer again to the top layer. So what happens? So as you can see here, we have a more like a multi-graph environment. And then if we search a vector, if the vector, for example, lands here, the algorithm has always the same entry point on the topmost layer, and then we'll search the vector that is the closest to your search vector. And then we'll use that vector as entry point in the layer underneath, and then we'll go to the closest layer again, and then we'll use that again as an entry point in the bottommost layer. And like this, you can see you're skipping a lot of steps, checks, or nodes, so to say, in graph theory, to find the closest vector that you're searching for. And that really allows them to really search for millions upon millions of vectors within millisecond response time for you. And this is only one algorithm out of all the algorithms they built. So again, you'll see same entry point, searches the closest vector to what you're searching, uses that vector as entry point, goes to the closest point again, uses that vector as an entry point or object, and then goes to the closest one. So you can see if we were to start here and have to go evaluate all these steps, it would take significantly longer. Which is pretty cool, if you ask me, pretty smart. All right. So let's get to the cool stuff. Let's build our own search. Anybody recognize what this is from? Sorry? John Wick. Almost. The Matrix. Same actor, different movie. It's okay. But in John Wick, he also said, "I need guns, lots of guns." He's rehearsing his lines, and nobody's noticing. Anyway, so Neo in the Matrix. Who has not seen the original Matrix? Interesting. So he asks for guns, lots of guns, but there is like a plot hole here. How is he ever going to find the guns he needs in this mess, right? So we're going to help him. We have a small CSV with some weapons. The weapons have three properties: name, type, and range. For example, Excalibur, sword, and short. And then once we vectorize that, basically the embedding module will grab all the properties, create one string out of it, lowercase, a weapon, Excalibur, short, sword. You can even choose if you want to vectorize the property names. Then it would be weapon, name, Excalibur, type, range, short, type, sword. And then we get a vectorization out of that, which is 384 dimensions. All right. Yes. So Trinity walks to Neo. Is like, what the hell are you doing? There's no way we can save Morpheus. And it's like, I'm cool. I can do whatever I want. I have plot armor. What weapons should we search for? Anyone has any idea? An Uzi. A Webley. You come out, which is also a pretty small weapon. Anyone has a favorite weapon? How about I want a Japanese weapon. And then you get an Odachi, which is in fact a Japanese weapon. Any other ideas? A longbow. I need a longbow. There we go. Yeah, I had that one. Nice.
A weapon with wheels.
A weapon with wheels. You just go for the nuclear solution. A Lilliput. So let's see. So the distance of the Lilliput from the weapon with wheels was 0.53. I have a 0.99 cutoff on the distance. And for example, the longbow, the distance was 0.2, and the Japanese was 0.4. So you can see it was a little bit, I don't think I have a weapon with wheels in my data set. So what I could try, last one, an explosive weapon. And the beauty is you don't really care about typos, mostly. An RPG, which is indeed an explosive weapon, you could say. And you know what the beauty is about vector databases is when you do a search, you never really know what you're going to get out of it. And to me, that's really beautiful. You just send in something and you get something out, you're like, okay, yeah, well, fair enough, makes sense, I guess. But given the same search, they guarantee you always get the same result. But what that result is, you never know. And if you're a little bit of a gambling addict, like, then you like those kind of things. All right. Do we have any Dungeons and Dragons enjoyers here? Yeah? Great. A long time ago. Well, maybe you should pick it up again. So we're going to have a wizard. He's strolling through the woods. Then suddenly he's ambushed by a thug. He's old and doesn't remember which spells he knows and which spells he doesn't know. So we're going to be helping him to find spells to cast. So we're going to just put in things, and I have like the whole data set of Dungeons and Dragons spells loaded in the database, and then let's see what we get out of it. And using a BERT model, we'll get one of the spells out. I did need to do a little bit of data preparation here, because if you look at the CSV for this, a little bit spoiler of what's coming, I guess. This is how the CSV looks like. So it's very it's really ready for a computer to read it, so to say, but not necessarily to search it semantically. So what we did is basically I created a descriptor that reads very semantically. So for example, this spell can be casted by these classes, this is the level, etc., etc., etc. And then I said, okay, I want you to just vectorize the description and the name of the spell. Do not vectorize all the other properties, but they're still in the database. So when you retrieve the object, you still have all those properties, then you can use them for whatever you want. All right. So guys, imagine you are a wizard. What would you want to cast to save yourself? Sorry? Disintegrate. Do you write it like this? I don't know. Disintegrate. And then, of course, you can cast it and then that. Anything else?
Make him dance.
Make him dance. Otto's irresistible dance, then? There we go. I know the animation is exactly the same. We'll get to that, okay? Okay, last one. Sleep. Put him to sleep. Dream, I bite, a catnap. And I do know that I bite is actually a sleeping spell. So yeah, as you can see, it's pretty accurate, right? You don't really know what you're going to get out, but once you get out, you're like, okay, well, yeah, I guess this makes sense. All right. But that is text, and text at some point gets a little bit boring, so let's talk images. Anybody played this, Pokemon Snap? Why? Why? It really, you're on rails, and they drive you around, and you take pictures of Pokemon, and that's it. But it was hugely popular, and I think the newest version is still very popular. So what we're gonna just remake it with a fear of getting sued by Nintendo. So we have Ash, which flips his cap when he sees a Pokemon, and then we're gonna take a picture of that Pokemon, which will be vectorized using a ResNet 50 model, and hopefully we found the Pokemon we'll be looking at. All right, so. Yes, I know that you feel like you've been transported to the anime right now. It's not the case. Who knows which Pokemon this is? I hear a lot of laughing, but no one is saying it. Yeah? Pikachu? Let's see if the database agrees. Which is indeed, it is Pikachu. Well done. Do we have any Pokemon masters here? No? I was at a conference some time ago, and there was a person asked, "Are Pokemon masters?" And I said, "Yeah, sure." Okay, what is number 178? And it was like, "Yeah, that's it." And it was right every single time. Very, very impressive. All right, so let's go to another one. Does anybody know which Pokemon this is? I heard Stinger. No, that's not it. Beedrill, yes. But the database disagrees. It's Kabutops. I'm sorry, man. So what if we try again? No, now it's Prinplup. Whatever that is. And then, so that was a little bit of a fail, you could say. So if I walk around, wait, where am I? Oh, here. Does anybody know which one this is? Mew. The cute one, right? No, it's Drifloon. So it's not working very well, right? If you look at the data set that I use for the Pokemon, so I have a data set from Kaggle, amazing website, open source data sets, and they have a picture of all the Pokemon. And this is how the picture looks like. This is, for example, Charizard. This is Beedrill. This is Pikachu. And as you can see, there's some things that make these pictures not very usable. For example, there are always one picture, one pose, and it's very cartoony, so to say, while our game world is more 3D. And the pictures are always with a white background. And the embedding module we use always defaults to a white background. Or black, you can choose, but it's always white or black. You can't have transparent, which is a little bit of a shame. So that means if it doesn't know, and the embedding module does not understand Pokemon, right? It does not know what a Pokemon is. So that means that once you do a search, it searches with a lot of white pixels would almost always match pretty much the whitest Pokemon out there. Because almost all the icons have like 40% of the icon are white. So you would always get a very white response. So to work around it a little bit, this is the camera that actually looks at the Pokemon. And it's very yellow. And as you can see, it is a very specific type of yellow. It's Pikachu yellow. Just to make sure, if I show you Pikachu, that you can get Pikachu. But yeah, so what I'm trying to say is, it is really no silver bullet. You can just put in whatever you want and we'll always find what you're searching. It really needs some data preparation. For example, in this use case, I should have probably, well, ideally, I would have trained my own embedding module that understands what a Pokemon is, right? And then it searches based on the context of Pokemon. Well, I don't have millions in my bank account. So another way to do that is actually use more images of the Pokemon. So multiple styles, 3D styles, multiple angles, and things like that, which would make it easier to match exactly the Pokemon searching for when I supply an image. So these are kind of the ways that you can do, or you can use to make your data sets more reliable, to actually find what you're searching for. You can also, if you want, you can also use a more hybrid search, so that the database underwater tries to match exactly as if it was like an Elasticsearch or whatever, and then also matches semantically, does combination of the two, and then gives you a result. That's also possible if you want to go that way. All right. So we have seen that you can vectorize images, you can vectorize text, but how about vectorizing both in the same vector space? Thankfully, there are models out there that allow you to do that. So our wizard is going to be ambushed again. He's forgetful, he walked a circle and he went back. But this time we're going to do something a little bit different. So we're going to still say, okay, this is the spell that you can use. But this time we'll be grabbing the name of that spell, and then we're going to supply it in a database of spell icons. And like that, hopefully match an icon that matches the name, or that is very similar to the name of that spell. And then we can use that, and then we do that through a clip model, OpenAI clip, and then hopefully something cool will happen. When we look at the icons, they look a little bit like this. So this is one of the icons, or this, or this, or this. So they're pretty high quality. They're all the same dimensions, 256 by 256. And most importantly, I bought these things like 10 years ago of a Humble Bundle. And finally, after 10 years, I got to use them for something. So that's pretty nice. But yeah, as you can see, they're pretty gamey, right? It's not necessarily something you would see in your everyday enterprise application. Or unless you work on a really cool enterprise application, I guess. Okay. So yeah, we're at the same moment. Anyone want to give it? Oh, before I ask you guys, I have a personal goal to every time I give a presentation to show an explosion. So I'll start with that. A fireball. and we search, and then indeed we get a fireball. And then the name of the spell, which is in case fireball, pyrotechnics, and firebolt, is extracted of response. Then we do a text search on an image, a vectorized vector space, and then we get the images back that match fireball. And I don't think anyone can argue that, you know, a fireball would probably look something like this. And then we can cast it, and then thank you. That was my explosion quota reached. Any other things you might want to see? Okay. Diarrhea attack? Delay contagion. Eye bite. Well, I guess contagion gets pretty close. I'm pretty sure there's not a diarrhea spell in Dungeons and Dragons. But a disease is probably pretty close to that. So if we cast this, then you can see it's a different color. So the diarrhea attack really launched him into orbit. And if we have icons, then you know, what you can do suddenly is you can extract average colors out of your icon, and then you can match particle effects on the average colors and stuff like that. So then suddenly it can be more than just the same animation over and over again. So yeah, let's do one or two more. Teleport. You want to?
Up into the air.
I need to teleport him. Let's see. So we have teleport, which does maybe, yeah, I think so. Or dimension door, which is, so which one do you want to, which of the three do you want to see?
Probably the first one.
Let's see what happens. Ooh, it's sparkly. And he did get launched into the air. And last one. A snowflake. Let's make it a little bit more high fantasies. I want to freeze him like a snowflake. Investor of ice knife, which is a knife, not necessarily an ice knife, or the freezing sphere. Do you have a favorite out of the three? The freezing sphere, let's see what happens. Oh, so so the average color was more black. So then I just do every color. I could do, for example, poison cloud. Then stinking cloud, yeah, which is way more blue. Or I can do disease. Is that how you write disease? I don't know. No. No. I wish it was like that. Which is very red. So as you can see, I match the average color and do a particle based on that. All right. We have 2 more minutes. Any metalheads here? Me. Okay. Anybody that really hates metal music? Is it Stefan again? Yeah. I'm sorry for the second time. So I'm a really big metalhead myself. And the big problem with metalheads is, or with metal music is, you hear the lyrics and you have no idea what they're singing, right? So okay, what if I make an application where I can just listen to the music and then I get the lyrics and the world is perfect? So I loaded the vector database with a lot of songs from Beyoncé, Billie Eilish, Coldplay. There's like a lot of stuff. Post Malone, Taylor Swift, Selena Gomez. And I have 3 metal songs in there. And one of them is the one we're searching for. Because do the metalheads know Metalocalypse? Well, it's a Duncan Hills coffee jingle. And that is like the international coffee anthem. You should know it, to be honest, but and that is the song we're going to be searching for. Anyone want to place a bet if we're going to find it or not? Who thinks we'll find it? Who thinks no way? Who thinks it depends? All right. So we are using OpenAI, an OpenAI model that transcribes the audio and tries to understand the lyrics. And on the top, you'll see the song we think is playing right now, based on the transcribed lyrics you see on your left. And on your right, the actual lyrics. Taylor Swift, Dragon Force, which is a metal band, Coldplay, I don't know. Taylor Swift, maybe she should consider a career switch, or maybe Selena Gomez. Closer and Further, I don't even know what this is. Lady Gaga, can go pretty hard to be honest. Ed Sheeran. Apparently, if you have a guitar solo, it transcribes as Ed Sheeran. I don't know why. Really transcribes as Ed Sheeran. And we end up with Selena Gomez. So as you can see, we did not find the song we were searching for. And to that, I have only one thing to say. If Skynet rises and AI takes over, we'll just need to grunt to each other, and there is no way they're going to know what we're saying, so we're pretty safe. Thank you very much. That was it.